Welcome back. Today we are focusing on a purely numerical approach, estimating limits from tables. While graphs offer a powerful visual intuition, sometimes a function is completely abstract, complex, or difficult to graph clearly by hand. In these scenarios, we build numerical tables to observe the behavior of the output values as the input values get infinitesimally close to our target number. Just like with our visual analysis, we must always analyze the approach from two distinct directions. From the left, using values slightly smaller than our target, and from the right, using values slightly larger. By calculating the function's output for closer and closer approximations, we can often identify a clear convergence pattern without ever needing to look at a plotted curve. This table-based approach forms the very numerical foundation of calculus. Let us thoroughly analyze example 1. Consider the function f of x equals the fraction x squared minus 4 in the numerator over the quantity x minus 2 in the denominator. We want to estimate the limit of this function as x approaches 2. Now, if you attempt to directly substitute x equals 2 into this algebraic expression, you will immediately encounter 0 divided by 0, a completely undefined state. The function physically does not exist at exactly x equals 2. However, we know that limits do not care about the destination point itself, we only care about the journey. To evaluate this limit numerically, we will construct a table of values zooming in on 2. We will start with a left-hand approach, carefully selecting x values that are slightly smaller than 2, and then we will construct a right-hand approach using x values slightly larger than 2. Let's build the explicit table for example 1. First, we examine the left-hand approach where x approaches 2 from below. We plug in 1.9 and the output is 3.9. We get closer plugging in 1.99 and the output becomes 3.99. We get even closer plugging in 1.999 and the output is precisely 3.999. Notice the undeniable mathematical trend. As our inputs slide closer to 2 from the negative direction, the outputs are firmly targeting the value of 4. Now, let's execute the right-hand approach where x approaches 2 from above. We plug in 2.1, yielding an output of 4.1. Getting closer with 2.01 gives us 4.01. Extreme proximity with 2.001 yields exactly 4.001. Here too, the pattern is inescapable. From the positive direction, the outputs are aggressively sliding down toward the exact same target value of 4. Because both the left-hand table and the right-hand table converge perfectly onto the number 4, we can confidently estimate that the two-sided limit evaluates to 4. Next, let's look at example 2, illustrating how numerical tables reveal when a limit does not exist. Consider the function f of x equals the absolute value of x divided by x. We want to find the limit as x approaches 0. Again, direct substitution yields the dreaded undefined 0 over 0. So we build our tables. Let's trace the left path toward 0. We plug in negative 0.1, the output is negative 1. We plug in negative 0.01, the output remains negative 1. Even at negative 0.001, the output is stubbornly locked at negative 1. The left-hand limit is definitively negative 1. Now, let's trace the right path towards 0. We plug in positive 0.1, the output is positive 1. We plug in positive 0.01, the output is positive 1. And at positive 0.001, the output is still positive 1. The right-hand limit is definitively positive 1. Comparing the tables, the negative approach yields a solid negative 1, while the positive approach yields a solid positive 1. Since these numerical targets do not align, the general two-sided limit fundamentally fails to exist. For our final advanced scenario, example 3, we must discuss accuracy and the dangers of numerical estimation. Consider the function f of x equals sine of the fraction pi over x. We will investigate the limit as x approaches 0. You might try to build a table and unfortunately choose test points like x equals 0.1, 0.01, and 0.001. If you plug these specific numbers into the function, your calculator will output exactly 0 every single time. A careless student might look at this table and incorrectly conclude the limit is 0. However, this is a dangerous illusion caused by poor sampling. If we choose a different sequence, say 0.015 or 0.0025, the outputs will wildly fluctuate between 1 and -1. The function is effectively oscillating infinitely fast, a phenomenon we previously observed visually. Numerical tables are incredibly powerful approximation tools, but they mandate extreme caution. You must select diverse, highly granular test points and always be vigilant for deceptive convergence patterns. Numerical estimation requires critical thinking, not blind calculation.